Hello and welcome to Fall Asleep to Science. I hope you will enjoy our lecture today. Let's get started. Ionization energy is the energy required to move the least tightly bound electron from a neutral atom in the gas phase. The periodic trend in ionization energy is that the ionization energy is lowest at the bottom left corner of the table and increases going up and to the right, with the highest ionization energy being for helium. This is the same trend as for effective nuclear charge, as well as atomic radii. A smaller radius means higher effective energy. The real reason that a half-filled subshell is so stable is because a half-filled subshell serves to maximize the stabilizing interactions, while minimizing the destabilizing interactions among electrons. Exchange interaction is the stabilizing interaction, and it is a result of electrons pairing in degenerate orbitals with parallel spin. The pairing energy is a destabilizing interaction, the Coulomb interaction, and it is the energy of electron-to-electron repulsion in a filled orbital. A higher energy electron is easier to ionize. It already contains more energy, so the input to remove it from the atom is less. If a D-series metal has the configuration 4s2, 3dN, the first electron to be ionized will come from the 4s orbital. The remaining s orbital will then enter a d orbital, giving the configuration of the +1 cation 4s0, 3dN + 1. The lanthanide contraction is the reduction in atomic radius following the lanthanide series, contrary to the overall trend observed for the periodic table. The lanthanides are elements 57 through 71 and are the first appearance of filled f orbitals. F orbitals are poor at shielding, so any electrons added to the subshell following the f orbital experience a higher effective energy, shrinking their radius over what is expected from overall trends. Slater's rules tell us what the effective nuclear charge will be. Formally, it is written as Z subscript EFF equals Z minus sigma. Z is the atomic number, and sigma equals the sum of SI, where SI is the number of electrons in a given subshell multiplied by a weighting coefficient. Shielding is the reduction in charge attraction between the nucleus and electrons, due to electrons between the nucleus and the electron in question. An electron is between the nucleus and an electron, being considered if it has a lower energy. Penetration is when an electron of a higher atomic orbital is found within the shell of electrons of lower atomic number. That is to say that an electron of higher energy is found within an orbital of lower energy. Electron affinity is the difference in energy for a neutral gaseous atom and the gaseous ion. It is used as interchangeable with electron gain enthalpy, which is the change in standard molar enthalpy when an atom or molecule gains an electron. A more positive electron affinity means that the atom is more stable with the additional electron, while a more negative electron gain enthalpy is indicative of greater stability. The total effect of electron affinity and ionization energy is known as electronegativity. It is the overall measure of an atom's ability to attract electrons to itself when part of a compound. Fluorine has the highest electronegativity. To explain electronegativity, Pauling's theory is used most commonly. Polarizability is an atom's ability to be distorted by an electric field. Basically, it means that regions of a molecule can take on partial positive or partial negative charge. Systems involving multiple electrons are much more complex, and they require the use of quantum mechanics, which is why we use the hydrogenic system approximation. The formula for the energy of a hydrogenic orbital is E sub n equals negative 13.6 times z squared over n squared. Here, 13.6 electron volts is the result of H times C times R and converting to EV. The negative is a result of the sign convention of energy levels. R is the Rydberg constant, which is 1.09737 times 10 to the 5 inverse centimeters. C is the speed of light in centimeters, 2.998 times 10 to the 10 milliseconds inverse, and h is Planck's constant, 6.626 times 10 to the negative 34 joule hertz. Wave numbers, which are the inverse of wavelength, are expressed as inverse centimeters and is another way of expressing the energies. The quantum numbers are n, l, m sub l, and m sub s. N is the principal quantum number. It defines the energy and size of the orbital. L is the orbital angular momentum quantum number. It defines the magnitude of the orbital angular momentum, as well as the angular shape of the orbital. L can have values of 0 to n-1. M sub L is the magnetic quantum number. It describes the orientation of the angular momentum. M sub L can have values of 0 to positive or negative 1. M sub S is the spin magnetic quantum number. This defines the intrinsic angular momentum of an electron. M sub S can have values of either positive 1/2 or negative 1/2. It can be seen from these definitions that every electron in an atom or molecule will have a different set of quantum numbers. The radial wave function, r, along with the angular wave function, a spherical harmonic, gives us the orbitals. With a wave function, it is possible to completely characterize a particle. The wave function does not go to 0 at the nucleus. They go to 0 at infinity. When graphed, these produce the characteristic shapes of the orbitals we are used to seeing. The radial distribution function is a plot of r squared versus the radius. It tells us the probability of finding an electron at a certain distance from the nucleus. Every orbital has a different radial distribution function, and a node on the graph is a region of 0 probability. Bohr radius is the most probable distance to find the electron in a 1-proton, 1-electron system. The orbitals that correspond to L equals 1 through L equals 4 are L equals 0 equals S, L equals 1 equals P, L equals 2 equals D, L equals 3 equals F, and L equals 4 equals G. The building up principle, or Hund's rule, is when degenerate orbitals are available for occupation, so electrons occupy separate orbitals with parallel spin. The Pauli exclusion principle says that no more than 2 electrons can occupy a single orbital, and to do so, their spins must be paired. Moving into molecular geometry, the valence shell electron pair repulsion theory, also known as the VSEPR theory, is to predict molecular geometries. The basic assumption is that regions of enhanced electron density take positions as far apart as possible in order to minimize repulsive forces. The relative repulsive strengths of electron-dense regions are: lone pairs are greater than multiple bonds, which are greater than single bonds. Valence bond theory explains chemical bonding by considering the overlap of atomic orbitals. The wave patterns of atomic orbitals interfere constructively to form a bond. A sigma bond is orbital overlap of atomic orbitals with cylindrical symmetry. A pi bond forms when atomic orbitals overlap side by side, after the formation of a sigma bond. Hybridization is used to explain bonding where the number of equivalent bonds exceeds the number of valence orbitals. The effect of a lone pair on geometry is that a lone pair pushes strongly against all other substituents. It is the strongest steric force governing the shape of a molecule. Molecular orbital theory is an improvement over valence bond theory in that the bonding description extends to all atoms in a molecule and handles polyatomic molecules easily. Atomic orbitals continue to form molecular orbitals, which are delocalized descriptions of electron distribution. Molecular orbital theory makes several key assumptions. The first is the orbital approximation. The wave function, describing all of the electrons of a molecule, can be written as a product of the one-electron wave function. Second, the linear combinations of atomic orbitals. The superposition of multiple atomic orbitals of the same type along with weighting coefficients. Orbitals of the same symmetry can and will mix. We can construct molecular orbital diagrams. The first are homonuclear diatomics. H2 and H2-like molecules fit into this category. Here, the 1s orbitals are of equal energy, so they lie at the same level of the diagram. The atomic orbitals combine to form 1 sigma orbital, which is lower in energy, and 1 sigma plus orbital, which is lower in energy. Another example are period 2, such as lithium 2 through N2. Since we're dealing with diatomics, the energy of the contributing atomic orbitals of each atom is the same. The two s orbitals combine to form a bonding 1 sigma and an antibonding 1 sigma, as well as a bonding 2 sigma, although that MO is mainly 2p in character. The 2p orbitals combine as follows. The lowest energy orbitals are 2 degenerate pi orbitals, denoted 1 pi. The next lowest is a single 2 sigma orbital, which has some 2s character. Next in energy are the antibonding orbitals, 1 pi, or doubly degenerate, and 2 sigma. Remember to order the molecular orbitals from lowest energy to highest energy. Period 2 also includes O2, F2, and neon 2. The only difference between this MO diagram and the preceding one is the relative energies of the bonding orbitals 1 pi and 2 sigma. They are reversed. Remember, again, to order the molecular orbitals from lowest energy to highest energy. Heteronuclear diatomics also exist. This is H to X. For simplicity's sake, this discussion is restricted to H bonded to something that bonds through 2p and 2s orbitals. Because we are now working with two different atoms, we need to take into account the relative energies of the atomic orbitals. In a molecule that is hydrogen bonded to some other atom, the H1s orbital will always be higher in energy than the highest energy orbital of the other atom. This is not a universal truth, but for molecules that actually form, it is a good rule of thumb. The 4 atomic orbitals of the X atom mix with the 1s of H to give 5 molecular orbitals. From lowest E to the highest, the order of the orbitals is 1 sigma, 2 sigma, 1 pi, doubly degenerate, and 3 sigma. The antibonding 3 sigma is mostly H in character, while the other 4 are mainly X in character. There is also an X bonded to Y. To properly construct this diagram, we need to consider the relative energies of the bonding orbitals of both atoms. The more electronegative the atom, the lower in energy its orbitals will be. So, for both the p and s orbitals, Li is greater than Be, is greater than B, is greater than C, is greater than N, greater than O, greater than F. The relative energies of the MOs are 4 sigma greater than 2 pi, greater than 3 sigma, greater than 1 pi, greater than 2 sigma, greater than 1 sigma. Polyatomics. In order to construct a molecular orbital diagram for a polyatomic, we have to use one of the approximations of molecular orbital theory. Linear combinations of atomic orbitals, also known as LCAOs, create a cumulative approximation of the atomic orbitals of its constituent atoms. The notation for LCAOs is as follows: B equals non-degenerate, E equals doubly degenerate, and T equals triply degenerate. To determine what orbitals will mix with what, compare the energies. To determine how to set up the LCAO, just remember that A is lowest in energy, then E, then finally T. For example, 3 H1's orbital and NH3 combine to form LCAOs of 1A and 2E's. They don't form one set of T LCAOs because that is not the order in which the orbitals are filled. Bond order is a method to assessing overall bond strength between two atoms in a molecule. It directly assesses the number of bonds between them. The higher the bond order, the stronger the bond. A bonding orbital will lie lower in energy than its substituent atomic orbitals. An antibonding orbital will lie higher in energy than its substituent atomic orbitals. A non-bonding orbital will equal in energy to its corresponding atomic orbitals. HOMO, or the highest occupied molecular orbital, is where the highest energy electrons reside. LUMO, or the lowest unoccupied molecular orbital, is the energy level directly above the HOMO. HOMO and LUMO interactions are critical to electronic structure. When an excited state is formed, an electron is promoted from the HOMO to the LUMO. The bonding and anti-bonding characteristics of the frontier orbitals are of great importance to the stability of the molecule. Basically, whereas in neutral atoms we treat valence shell electrons as the point of interaction, the frontier orbitals are the point of interaction and basis of understanding for molecular interactions. If there are two unpaired electrons, the species is paramagnetic. We will pause there for now, but I hope you will join me for another installment of Falling Asleep to Science. Thank you for listening.